students, in our previous video we have seen the electric flux and Gauss theorem. Today we will see how to apply Gauss theorem practically, that is called application of Gauss theorem. Okay, this is the basic expression for the Gauss theorem. If we will open it, we will write it E dA cos theta equal to Q by epsilon naught. Now by this expression, we can simply find the value of electric field by this expression. So the application, so we will apply this for first, suppose we have a wire, a long wire. It has some length, suppose this is L. Okay, and the charge are distributed uniformly like this. So because of this charge, we have taken a certain point with some certain distance, and we now want to find the value of electric field. So we just simply draw a line like this. If we want again to find the electric field in this point, we again draw a line like this. Suppose this is upward direction and we want to find in downward direction. We simply mark a point and draw a line. So these are the charges which are distributed, and these are the points where we have to find the value of electric field. So this distance should be equal. Why? Because the charge is distributed uniformly. So the electric field, if it will apply, that will be distributed uniformly, and we will form a cylinder. We will form a cylindrical surface like this. Where this point to this point will be same, the distance will be same. For this point to this point, the same distance we are measuring for both the points. So all charges are distributed equally with the same distance and applying the electric field with same distance. So this is the surface, that is curved surface. Okay, and this is the cross section area. Now in Gauss theorem, what we have seen two conditions for electric field and the area. If electric field and the applied area will be parallel, then Gauss theorem, the flux will be valid. We will get the electric flux. Not in Gauss theorem, in electric flux section we have seen this. Electric flux will be EA, because in this condition the theta will be 0 and the value of cos theta 1. So what we will find? EA. If the electric field and area both are perpendicular to each other, then the theta will be 90 degree. In this condition, the flux will be 0. We will not get the flux in this condition. So here you are seeing in curved surface, this has some area, this surface has some area, and it is applying in this direction, and the electric field is also applying in an upward direction. So the both are in parallel. So in this condition, we will find the flux. But if we will see in this direction, this has area which is in this direction, that will be perpendicular, but the charge will distribute in this direction. So this is making 90 degree angle. The both are perpendicular to each other. So in this condition, we will not find any electric flux. Okay, so in this position, if the charge is in this position, then we will find the electric flux. This is clear? Just note it down or take a screenshot. I'm going to rub it. Okay. So the first condition in application of Gauss theorem is we will find the electric field for due to uniform infinite uniform charged wire. Okay, so this was the wire. It is placed in a cylinder, in a cylindrical surface. It should be equal. This is the charge which are placed uniformly distributed here. And the length of the wire is L. This is R. This distance we are taking R. Okay, so by Gauss theorem, we know and cos 90 we simply put, cos 0, because theta in this condition is 0. So cos 0 we simply put equal to Q by epsilon naught. Now the value of E is KQ upon R square. So this R is uniformly distributed. If this is the distance R, so this will be the distance R, this will be the distance R. In downward direction is also, it has R distance, it has R distance. So the distance R is uniformly distributed. So we can take it as a constant. Q is distributed in all surface and it has same magnitude. So we can take Q as a constant. So then E will come out. And K having a constant value, we know that is 1 by 4 pi epsilon naught. Now what we will get, integration of dA in this Q by epsilon naught. In the form of charge density, the term charge density, what is charge density? Sorry, I forgot to explain. Let's just see a quick explanation of charge density. Charge density we will find in three conditions. First, for any linear field, suppose there is a field, it has an electrical field, so it must have charge. Q is distributed uniformly in any field. Suppose we have a wire, it has some length and the charge is distributed uniformly. So the charge density is describe the accumulation of the charge in any field. So the density, if we will denote it by lambda, that is charge density. So the lambda is equal to, for uniformly distributed charge, this is uniformly distributed charge, the lambda is Q by L. Okay, this is the first condition. This is for the linear distribution. Suppose there is a surface charge density, if we want to find for any surface, there is another formula, that is, we denote it for surface charge density. This is linear charge density, just note it here, linear charge density. This is surface charge density. Okay, so that will be, we denote by sigma, that is always equal to Q, again the distributed charge, upon area. If it is in terms of surface, it has some area. Either it is square, it is in a form of rectangle, any kind of area. Now, volume charge density. It has simply some volume, either cube, cuboid. So we denote it by volume charge density, we denote it by rho, and rho equal to Q upon V. Simply, these are the formula. Rho equal to Q by V. So for linear charge density, lambda equal to Q by L. For surface charge density, sigma equal to Q by A. And for the volume charge density, rho equal to Q by V. This is the basic formulas. Now from this formula, we can simply put Q equal to lambda L. This L will cross multiply with lambda, that will be Q equal to lambda L. So now we will put here Q equal to lambda L. So this will be E dA equal to Q. In the place of Q, we will put lambda L upon epsilon naught. Now area of dA, this is a cylindrical surface. So we know the area of cylinder, that is 2 pi RL. We simply put here E into 2 pi RL equal to lambda L by epsilon naught. Now this will go in this side, then it will cross multiply with the epsilon naught. So this will be lambda L upon epsilon naught into 2 pi RL. Just note it down, I'm going to rub it. Otherwise in this here it will not clear. So E equal to 1 by 2 pi RL into lambda L upon epsilon naught. If we will multiply 2 in denominator and numerator in both, so what we will get, that will be 2 lambda L upon 2 to the 4 pi epsilon naught RL. This L cancel out. Then what we will get, the 1 by 4 pi epsilon naught is the value of 1 upon 4 pi epsilon naught is K. So we can put here K in the place of this, that will be 2K lambda upon R. That is the electric field for the infinite uniformly charged wire. Now we will see the electric field due to infinite charge sheet. Suppose we have a charge sheet, that is the charge sheet. It has charge which are distributed like this uniformly. Suppose this is sheet, so it will apply the electric field in this direction, same in opposite direction, right? And I just appear, this is the sheet and I am just appearing a cylinder like this. So cylinder will appear in the sheet like this, and then it has charged. Okay, now because of this cylinder, we will see the charge. This is the curved area. This is the curved area. So because of this sheet, the electric field will be in this direction. And if we will see the area of this curved surface, that will be in perpendicular direction. So this angle will be 90 degree. So in curved surface, the area will be, the flux will be E. Wait, marker is not working. Let me change the marker. That will be EA cos 90. The angle theta will be 90 degree in this condition. So what we will get? We will simply get EA. This is cos 90. So this will become 0. Cos 90 is 0. So this will become 0. So in this case we will not get any flux. Now in the cross section area. So here the direction of the electric field is in this direction and the area of this cross section will be in this direction. So both will be in parallel. Then theta will be 0 degree. So the flux will be EA cos 0, which is EA because the value of cos 0 is 1. So in this condition we are getting phi. So now we have clarity of it that we will find the electric field. We will find this theorem will apply here in the cross section area. So we simply apply Gauss theorem. That will be EDA plus, you are seeing two cross section are here. So we will add it 2 times. That will be EDA equal to Q by epsilon naught. Now in this context we are talking about area. For area, the density, the charge density is, that will be sigma equal to Q upon area. So by this we will get the value of Q expression is sigma A. So we simply put in the place of Q, that will be sigma A upon epsilon naught. Another value of EDA we have just seen. What was that? EA simply. Again EA. Because if we will open it, that will be EDA cos theta, and cos theta is 0 degree, theta is 0 degree. So cos theta will be 1 and we will get simply EA. So this will become 2EA equal to sigma A upon epsilon naught. This A will be cancelled out. So the value of E we will get, this 2 will come and multiply here. That will be sigma upon 2 epsilon naught. This is the field. Electric field due to infinite charge sheet. This is the second application of Gauss theorem. Just note it down. Now we will see the third application. Application is electric field due to uniformly charged spherical shell. Okay. So this is the shell. Simply spherical shell. We are talking about spherical shell. We are not talking about solid sphere. So this will work as a hollow sphere. It will work as a hollow sphere, and if it is hollow sphere inside the shell, there will be no matter. If there will be no matter, so the charge will not lie here. It's very simple. So here we will see two conditions. First, we will find the electric field inside the shell, and second, we will find electric field outside the shell. If it is a sphere, it has a radius. The all charge will distributed in outside the cell like this. This is the charge which are distributed uniformly. Suppose the radius is r, and this will be for every point. If we will measure it This will be R, this will be R, capital R, because this is making a circle. Now what? Now we will simply find out the Q in terms of density. We know if it is a spherical shell, so which type of density we will find here? It's a area charge density. This will be area charged density. And what is the area charge density? We denote it by sigma equal to Q by A, Q by area, charge upon area. And area for this spherical surface is, this is capital R. For a spherical surface, the area is Q upon 4 pi R square. So simply we will find the Q. We cross multiply this. That will be 4 pi sigma R square. Okay, we get this Q. Now we will see the first condition, when the Gaussian surface will be placed inside the shell. Okay, just take a screenshot. I am going to rub it. Okay, now we are talking about first condition. Just see it here. This is the spherical surface. The radius was the capital R, and we are considering inside the surface there will be a Gaussian surface. This is the Gaussian surface that is lying inside the shell, and we are taking this radius by this Gaussian surface is a small r. Okay, we are simply taking it as a small r. Now we are applying the Gauss theorem. Gauss expression is E into dA equal to Q upon epsilon naught. Now I have just told you that this will work as a hollow sphere. If it is hollow sphere, there will be no matter inside it. If there will be no matter, so how any charge will apply in this Gaussian surface? There will be no charge. If there will be no charge, so the Q will become 0. If the Q will become 0, then definitely the electric field inside the shell will be 0. This is very simple. So you just remember this concept. If we will talk about any spherical shell or any hollow sphere, then always electric field will be 0 inside the shell by applying Gaussian theorem. Is it clear? Now we will see the second condition. Just take a screenshot. Now this is the surface. Now we are taking second condition. When the electric field outside the shell, suppose now this is the Gaussian surface which are lying outside the surface, and we are simply taking the radius smaller again. Now this surface is outside the shell. Now again we will apply Gaussian theorem, that is E dA Q upon epsilon naught. We will open it, that is E dA cos theta Q upon epsilon naught. Now here theta will be 0 again. Why? Because if you will see in any point, the electric field apply in this direction, in this direction, in this direction, because charges are distributed here uniformly. And if you will see any section, any small section in this shell, that will be dA, and dA will be applied in the same direction. So both are parallel, which means theta will be 0. If theta will be 0 degree, then we will get simply E dA equal to, here the value of Q we have just found it. That will be 4 pi, what was the value? 4 pi sigma r square. That was the value of Q, 4 pi sigma r square. Now we will put here, that will be 4 pi sigma r square upon epsilon naught. Now here, what we will put, E will come out, it will work as a constant, and this will be summation of dA equal to 4 pi sigma r square upon epsilon naught. Now I'm going to write here. So this EA and this will become, what we will take? We will take the radius of outer shell, the Gaussian surface which is lying in outside this shell. We will take that area which is 4 pi small r square. It is also working as a sphere, so the area will be simply 4 pi small r square. So we will put here 4 pi r square equal to, this will be 4 pi sigma r square upon epsilon naught. Now 4 pi will be cancelled out. So the electric field we will get equal to sigma capital R square upon epsilon naught small r square. This will be the third application of Gaussian theorem, where we have found the electric field due to a uniformly charged spherical shell. There was two conditions. First was when Gaussian surface will lie outside the shell and it will lie inside the shell. For inside the shell, the charge will become zero because it will work as a hollow sphere. And for outside the shell, we will get this expression. Just note it down. Now you